Okay, we are now recording. So jumping back into yesterday's, not yesterday, 2 classes ago, let me find the presentation. I can always edit this part out. Okay. So let's zip back to where we left off. Okay, here it is. So we left off last time that impulse is a force over a duration of time, which causes a change in momentum. And we talked about the units that we would use for impulse, which is the same thing as a change in momentum. So we could also use kilogram meters per second or Newton seconds, either one. All right, so today I want to show you a graph, and this talks about the difference between a short period of time, which means a large force, in order to cause the same impulse. So what you're looking at here, this curve, this is all the different possibilities for a given impulse. For example, without an airbag, you would be up in this range right here.
I can't see anything. I don't know if you're presenting.
I don't think you're sharing your
Why
screen.
did this work? You're right. It's Monday. Okay. You can see it now, right? So this graph, what you're looking at here, is all the different possibilities for a certain amount of impulse. We have a choice: a large force and a small time, right? That would put us in this region right here. Notice how we have a small time interval, but look at how big the force is. We could have somewhere in between. We could lessen the force and lengthen the time a little bit. We could put it right about here. Or finally, we could extend the time as long as possible and look at how small the force got. It's way down here on the scale. We're way down here. So graphing really tells a good story. And we talked about airbags. We're going to talk a little bit about a bat hitting a baseball. In a few more slides, we're going to get to that. So I'm going to skip over the airbags because we kind of talked about that. Okay, so hitting a baseball. Well, there's going to be a given force and a time interval where the ball is in contact with the bat. So this F, this is kind of limited to the ability of the ball player, how much they swing, how fast they swing, how strong they swing. But this, the time, this is a matter of follow through. So if the ball player can keep the ball in contact with the bat longer, just a little bit longer, then they can get that momentum change larger. So the batter swings with a given force, and the ball is approaching the batter with a positive momentum, right? The batter's job is to not only reverse the momentum that the pitcher put on the ball, but then to send it back out in the opposite direction. It's a lot more complicated than this, but if you want to read about The Physics of Baseball. There's a good book. Robert Adair wrote this. It's called The Physics of Baseball. All right, so the batter wants to maximize the time that the bat is in contact with the ball. When they apply a large impulse, they're going to reverse the ball's large momentum from the pitch. Right? So the pitch is coming in, it has to be reversed. And this is a double effect, right? Not only are we stopping the forward momentum of the pitch, that's like the airbag example, but then with the continued follow through, then the ball now is given momentum back out towards the outfield. So we're going to skip over some of these questions. These take a long time. But notice these buttons here. If you go into Canvas and open up the PDF that has these slides, you can click on these answers here, and it will take you to a short video that explains the whole problem. All right, so there's that resource for you if you wish to take advantage of it. Okay, whoops, I lost my place now. All right, I'm not going to do that again because it takes a while to find where I was if I didn't make a note of the number slide I was on. Okay. Next section. Okay, graphical interpretation. I showed you one graph with a curve on it. Well, let's say we have a constant force over a certain amount of time. We can use graphics to calculate the impulse. It's simply force times the duration of time. And that makes a rectangle. And the area of that rectangle represents F times T, or F times delta T, rather. So base times height, right? This comes in handy when this force is not constant. What if we have a changing force? For example, look at this graph. Suppose the force is increasing for the first 3 seconds. Then it's constant from 3 to 6 seconds. Then it decreases to second number 7, and then it's constant for second 7, 8, 9 to 10. So we have this duration of 10 seconds with a changing force. It would be crazy to try and calculate that without graphics. But now that you see it here, we can use the area method. So quite simply, take the first 3 seconds and make a triangle, and you can calculate the area of a triangle, right? 1/2 the base times the height. The next section is a rectangle. And then from 6 to 7, from second number 6 to 7, it's simply a triangle piece right here, and then a rectangle below. You can add those two together, and then the final section is a small rectangle. So let's break this into pieces, shall we? All right. So suppose I want to make a triangle here. I'm just going to use this line tool to make a sections here. So we have a triangle, rectangle, Here we have a rectangle and a triangle. And it's quite easy then to calculate the area for each one of these sections and then add it up. You know, you have the area of this triangle here, this rectangle here. We have a rectangle over here. And a triangle here. Okay. So suppose we wanted to know just the first 6 seconds. Well, then we just take these two sections here. The triangle and the rectangle. Just do these two. Up to 6 seconds, you've got, let's see, 1/2 of 3 times 30 is 1.5 times 30, that's 45, right? Plus 1, 2, 3 times 30, that's 90. So 90 and 45 is 135. So answer B would be the time interval from 0 to 6 seconds. You'd use the area method to do it that way. Easy, right? All right, so this one is a similar question. From 6 seconds to 10 seconds, you'd simply do area from here to here, 6 to 10. So what do you have? You have a rectangle, right? Easy area, and you have a triangle. Triangle and a rectangle, add them together. Let's see, what would you get here? You'd get 2, 3, 4, 5, 6 times 60. I think it's 60. But you can check your answer here. Okay, let's move into some more interesting stuff like the momentum of a system of objects. Okay, system meaning more than one object. You could have a system of 2, 3, 4, however many is in the system. So what we're going to do is we're going to add up the momentum of each individual part, you know, taking direction into account. Direction matters. So we use vectors. It does matter if, let's say, you have one object going to the left and you have one object going to the right. And if this is the system, I draw a boundary around it. We could call this positive momentum and this is negative momentum. If these two are combined, they could be 0. Right? So these could be 0 if they're equal. Equal and opposite, they could add up to 0. So we have to use vectors. Direction matters. So here we have positive to the right, negative to the left. Let's use these assumptions as we move forward. For example, 6 kilograms going to the right at 13 is 6 times 13 for momentum. 14 kilograms going to the left at 7 is a negative momentum, right? 14 times 7. So what we do is for the system, we take the positive 6 times 13, we combine that with the negative 14 times 7, and we get an overall total momentum for the system of a negative 20. Right, so this red one, this is stronger than the 6. Overall momentum of these two objects is negative 20. So here's a problem that you can go through yourself and check your answer. Here's another one. A system of two objects. And you can go through and check for those answers. I don't want to take class time doing these. This is available for you. And finally, we get to this notion of conservation of momentum. Okay, simply speaking, this means that the total momentum of a system will remain constant as long as no external force is added. So going back to, let's say, these two, if these two collide, and I draw this boundary around the system, then the collision will not add or subtract any momentum for the total system. It will remain at negative 20. Why is this useful? Well, we know that if the 6 collides with the 14, then afterwards, if they stuck together for some reason, if they got stuck together with Velcro, then the combined mass of 20 would be moving to the left with this momentum, and we could calculate its final speed. We could calculate the final speed of these two after they get stuck together. Pretty cool. Let's see this demonstration. I actually haven't looked at this myself. Let's take a peek. Doesn't seem to be working. Perhaps this link is working. And it's not. Okay, we're going to move on. So what I described was a closed system, meaning we looked at the boundary around the objects and we didn't allow anything in and we didn't allow anything out. We looked at what happened inside. This is very important. We cannot allow any forces coming in from the outside, and we can't allow one of these objects to escape the system. We call that a closed system. And if it's closed, then momentum is conserved. Okay, momentum is not created. It is not destroyed. The total stays the same. The only way that we can change the momentum of a system is to introduce an outside force. Okay, what does that look like? So we have two billiard balls. Let's say we have a red and a green. They are heading towards each other with it. This one has momentum to the right. This one has momentum to the left. Well, after the event, after they hit, let's say this one bounces to the left and this one bounces to the right. We have momentum of this object and the momentum of this object after the collision. Well, if you keep track of these two momentums, the total will be exactly the same as it was before the collision. So we write this as momentum before plus impulse equals momentum final. What happened here, though, is there an outside impulse? Let's say this is 0. No impulse from the outside. We will get the momentum of the system before is equal to the momentum of the system after. Okay, so this could be 0, and they could be before and after being equal. Okay, keep in mind that this impulse has to be 0. All right, let's keep going. Types of collisions. All right, there's different ways that things can collide. They can be stuck together. They can be blown apart, like an explosion. Or they can also bounce. All right, here are the terms. Inelastic collisions. Inelastic means the two objects collide in such a way that they get stuck together. And some of the kinetic energy becomes heat or sound, right? You can hear them, or you can actually measure the temperature increase. Elastic collisions, that's when they bounce. Okay, think of billiard balls. They tend to be elastic collisions. They don't stick together. And then finally, explosions. This is when something is completely stuck together in the beginning, and then it breaks apart because of energy stored in one or two objects. Like there's a spring in between them, and you release them, and they fly apart. All right, so inelastic collisions. Let's take a look at what that looks like as compared to elastic. Okay, and I mentioned explosions. Picture's worth 1,000 words, so here we go. So which would this be? A and B are heading towards each other. They collide, and then they bounce, and they go back out. Which one would this be? Would this be inelastic, elastic, or an explosion? Let's pause here. I'm going to ask the group. What you're looking at here, is this inelastic, elastic, or an explosion? Put your word in the chat, and let's see how you do. Is it inelastic? Here's your choices. Elastic, elastic, or explosion. Okay, there's your choices. And I'm going to give you the visual again, not that one, this one. Okay, let's see what you said. Elastic, good. Yep. That's the bouncy one, right? So the bounce is elastic. All right, let's move on. What would we do to calculate momentum here? Well, we take the momentum of A plus the momentum of B, get that total. That's before the collision. After the collision, we take the momentum of A and the momentum of B and look at that total and set them equal to each other. Notice this little notation prime right here. This is just shorthand for it means after the collision. Whereas without the prime, this is before. So this is how you recognize before and after. Okay. Perfectly inelastic collisions. Okay. This is when A and B collide and they get stuck together. Imagine A and B are covered with Velcro. They hit and they get stuck together. Well, this still works. Momentum A plus momentum B before the collision is equal to momentum A plus momentum B after the collision. Well, the interesting part about this is that the masses are stuck together, right? They can be considered now as one big combined mass. And since they're stuck together, they are moving together. So they have a common velocity. We call that V prime. So after the collision, we can just use this single mass and this single velocity. And it's going to be equal to the sum of the two momentums before the collision. This comes in handy when I want to know how fast the combined lump here, AB, is going to be moving after they collide. Okay. For example, if we have a freight car at a known speed and it collides and couples with another car, right? Couples means it gets locked together. Well, if the second car is initially at rest, then it had zero momentum. The other car had 13,500 times 4.5. So we know the momentum of the first car. We know the momentum of the second car was zero. We know the mass of the second car. We can calculate the speed of the two cars after the collision. We simply take the total momentum before, which is 13.5 times 4.5. Take that and then divide it by 25,000 plus 13.5. Take this is the lump sum of the two masses, 13.5 and 25,000. And then we know the V prime, velocity after the collision. Click on this answer here and it will play the solution for you. Okay, here's a similar question. Here's one where we have a skater on ice skating towards her friend who is standing still. And as they collide, they hold on to each other. Well, now you know how to calculate their speed after the collision. Finally, we have explosions. And an explosion is exactly what it sounds like. If you took A, B stuck together in the beginning, and you had a little firecracker in between A and B, and you exploded it. Boom. A goes this way, B goes this way. Well, this is simply the reverse of the collision where they got stuck together. It's simply the reverse. So it doesn't really matter before and after, right? You know they're equal. So does this look familiar? We have the lump sum of the masses times the velocity. before the collision or before the explosion is equal to these two individual momentum of A and momentum of B. Okay, this was reverse of what we had before. Okay, this comes in handy when you're talking about firing a cannonball from a loaded cannon. Consider that A is the cannon and B is the cannonball. There's an explosion inside, and then the cannon kicks back a little bit. We call that recoil. And the cannonball gets launched in the opposite direction. Okay, so you can do this problem and check the answer. Same thing works with railroad cars. If they are at rest and stuck together to begin with, and then if a small explosive is set off in between them, it will blow them apart, and you'll know how they're moving. Depending on their masses, you'll know how they move. Okay, elastic collisions. This is the easy one. It's simply a bounce. A and B collide, and then afterward, A bounces and B bounces. Now they're in opposite directions. Conservation of momentum, same. Momentum of A plus B before the collision is equal to the momentum of A and B after the collision. Let's ignore kinetic energy for now because we haven't studied energy yet. So we'll just ignore this part. Focus on the conservation of momentum. Okay. I'm going to stop here so we have some time. Let us go into Canvas and grab the classwork for today.